So in the last video, we looked at Pythagorean theorem, right? So we're able to relate all three sides of a right triangle. Now, for trigonometry, we're trying to relate sides and angles of a triangle. And so we're going to introduce angles in both units, degrees, and radians. So I think the concept of degrees is pretty easy to understand. But the concept of radians is a bit more abstract. We don't typically on a day-to-day basis talk about things in units of radians. But from engineering perspective, radians are very, very useful. And we'll see why that is and try to clear up any confusion from the first time you may have learned about degrees and radians. And if it's still confusing, this video should clear it up. We're going to look at it from the perspective of a unit circle. So we're going to start by talking about one aspect of a unit circle, and we will look at the unit circle again in the next video when we introduce sine and cosine. You know, even at the college engineering level, I tell students to draw this unit circle because you don't have to memorize everything about sine, cosine, and the derivatives. You see that all of that information is contained within that unit circle. So it's very, very useful to understand the fundamentals. We're just going to look at one aspect of this unit circle to help us understand how we're going to use these angles in both degrees and radians. Okay, so when we look at the unit circle, here's our circle, and we think about the horizontal as our x-axis, the vertical as my y-axis, and the origin being at the center of this circle. All right, so we define an angle on this unit circle as being positive, going counterclockwise from the positive x-axis. So it's going in this direction here. That's a positive angle. If we reverse directions, we would call that a negative angle. And obviously this oscillates, and we'll talk about oscillations in a future video. But for now, we'll just look at one cycle here, right? So this green line is wherever my object or the point of interest is at. And so that's where this angle theta is going to. We specifically call this a unit circle, unit meaning one, because we force the radius to be 1. Now, it won't be immediately obvious why this is useful to us in this video, but when we look at the unit circle again, when we look at sine and cosine, and we tie it back to the Pythagorean theorem and the triangle, this would make a lot more sense of why the circle specifically needs to be a unit circle. For now, we're just looking at the concept of angles. So we're going to define the angles from the positive x direction in the counterclockwise direction. Remember what we defined as 90 degrees, right? So in the previous video, we looked at a right triangle, and we said when we have a horizontal line intersecting a vertical line, we have a 90-degree angle that's created there, right? 90-degree angles are very useful. It's a good reference point. We see a bunch of 90-degree angles shown by the intersection of the x and y axes shown here. So it's a good reference point if you're trying to define and explain what the angle is. Is it acute angle, right, less than 90 degrees, or it's an obtuse angle, larger than 90 degrees? Very, very useful to help describe angles in a general form. So 90-degree angle is a useful one to kind of walk all the way across from your positive x-axis. So like I said, here we have 90 degrees. If I go from the positive x-axis to the positive y-axis, that's 90 degrees. If I go from the positive x-axis all the way to the negative x-axis, I get 90 degrees from this first quadrant to this next quadrant over here. It'll be another 90 degrees. So this is 180 degrees. So when we have a straight line, this forms a 180 degree angle. If I go from positive x-axis all the way to the negative y-axis, I got 90 plus 90 plus 90. So 180 plus 90 is 270 degrees, right? So this angle is 270 degrees. You could say this is also negative 90 degrees if you just go in the clockwise direction. But for now, we're just going to go in the counterclockwise direction. And then if I go all the way from the positive x direction all the way back to the positive x direction, do a full cycle, that's 360 degrees. And so you're probably familiar with that one, right? So 90 degrees, 180 degrees, 270 degrees, and 360 degrees. And then we repeat. So 360 degrees is the same thing as 0 degrees. And then it repeats and repeats and repeats. So you can see the oscillation component of it. And in a future video, we'll focus on oscillation and how we look at it from the perspective of angles. Now, 90, 180, 270, and 360 are not the only important angles. Some of the other important angles are 45 degrees, 30, and 60 degrees. When I say important angles, these come up a lot as reference points, but they also come up a lot in how we design things in engineering. And in a second, I'll show you why these come up a lot. Okay, so 90 degrees, 30 degrees, 60 degrees, and 45 degrees. These are very, very common angles that show up, and any combination of them is useful, right? So 90, 180, 270, and 360, plus or minus 30, 60, or 45, right? Any of those are very useful. And here's the reason why. It's all about triangles, right? So you can think about the unit circle, and you're just building triangles within that unit circle. And we're using the, where we're looking at an angle, we're just basing that as your origin and building different angles there. So obviously this one would be looking at this angle here, 90 degrees, right? Triangles show up all over the place in physical systems as well as like forces. And we'll look at a lot of examples where we have 90-degree angles. Isosceles triangles. You probably have learned about isosceles triangle years ago. Remember, this just means that we have two sides of the triangle that are equal to each other, right? So this is not a right triangle in this form, so we would not use a Pythagorean theorem. But when we have two sides that are the same, we know that this angle and this angle are the same. What if I specifically make a isosceles right triangle? So in this case, we have two sides that are the same length, A, and we force a right triangle or a right angle there. Well, we know that this angle and this angle would have to be the same, right? So there's a number of things from geometry that would help us understand that. I'm going to assume that you know that, and you can visually see that these angles are the same. Remember from the previous video that we said that when you add all the three angles together, no matter what type of triangle we have, this will always equal 180 degrees. Okay, if that is true, then, and I know that this is 90 degrees because I'm forcing it to be a right triangle, then if I call this angle theta, and this angle is the same, right? Theta, so it's 2 theta plus 90 degrees is equal to 180 degrees. So 2 theta would equal 90 degrees, right? So 90 degrees plus 90 degrees, 180. So 90 divided by 2 would be theta, which is 45 degrees. So these angles right here are both 45 degrees. So whenever we have a right isosceles triangle, we get this 45-degree angle. 45 degrees also show up very nicely because 45 is half of 90 degrees, which we always see things, or we can build things easily in perpendicular to each other, meaning that they're 90 degrees from each other. So what about 30 and 60 degrees? So here we talk about isosceles triangle where we have two sides that are equal length. Equilateral triangles, if you remember, all three sides are equal length. If all three sides are equal length, all three angles would be of equal value, right? This, the sum of all three angles will be equal to 180 degrees, which means each individual angle would be the 180 divided by 3. So 180 divided by 3 is 60 degrees. So when we have an equilateral triangle, each of these angles is equal to 60 degrees. If I draw a vertical line, to split this, so that now I have a right triangle or right angle right there. So now I have two right triangles. So then I'm splitting this angle directly in half. So this 60-degree angle is now 30 and 30. So this side, 60 divided by 2 is 30, right? So this side's angle is 30. So a equilateral triangle split in half would give us a 30, 60, and 90-degree angle. This is why 30, 60, 45, and 90, and combinations of those up to like the 180, 270, and 360 show up over and over. So it's useful to understand the behavior of these. When we look at sine and cosine, we're going to really study what's the behavior of 30, 60, 45, and 90. Once we know just one quadrant, we can repeat it, and we'll use a unit circle to help us quickly get all that information. All right, so we've learned about some very useful angles in degrees, right? 0, 90, 180, 270, and 360. Those are all along the axes. And then we learned about 30 and 60 degrees from an equilateral triangle and splitting the equilateral triangle, and 45 degree for a right isosceles triangle. You've probably heard about the concept of a radian, and you know it has something to do with degrees. But why do we even use a radian as a unit? And why don't we just stick to degrees? Now, there's a very useful reason, right? So whenever we introduce concepts in math for engineering terms or just math in general, it's always for convenience and to make our lives easier. These are tools that are built to follow rules and simplify things. At least that's the goal, right? So understanding what the unit of a radian simplifies can help us use it more effectively. So when we look at a circle, and remember the radius is just half of a diameter, right? So we look to find the center of the circle, and we draw a line to any of the edge. The radius will be constant all the way around, right? So that's how we define a circle. Remember the circumference is the length of the line that defines this circle. That's different from the area. The area is a space that fills the circle. The circumference is this line that goes all the way across if I just measure that line, right? And hopefully you remember it's 2 pi times r, or the diameter times pi, because diameter is 2 times r. But let's think about it in terms of 2 pi r. Okay, so if the entire length is 2 pi r, I can define an arc length. So the arc length just means if I take a section of this curve, right, this whole circle, I'm only taking a small section and measuring that length. That's what we define as that arc length. Every arc length is related directly to the angle that created that arc. So for example, 45 degrees, this arc would be, let me see if I can draw it straight enough. So it would be this arc length right there, right? So that arc length would be related to 45 degrees. And I'm saying that we could take 2 pi r, the full circumference, and multiply it by a ratio. So if we talk about this in terms of degrees, we would need to take whatever theta is in degrees and divide it by the full circle, right? In which case we know that's equal to 360 degrees, right? 360 degrees is if I take a look and take an angle all the way across. This is 360. So for example, 45 degrees. So if I, want to think about what's this arc length, we can simplify this. I know 2 pi r is the full arc length, the full circumference. If I split this in half, you would expect it to be 2 pi r divided by 2. If you split it in half again, you would expect it to be 2 pi r divided by 2, divided by 2, divided by 4. And so 45 degrees is dividing it by half again, right? So we could put 45 degrees in for theta right here. And 45 divided by 360 is 1/8. And so 2 pi over 8 would be pi over 4. So pi over 4r would be this arc length. Pi over 4 times whatever that radius is. Because if you make that radius larger, you can see that the arc length would also grow. Okay, so why? Why am I introducing this concept? Well, wouldn't it be more convenient if I didn't have to multiply by this ratio every time I'm interested in the arc length? That is exactly where radians comes into play. So we say, I want to just define the arc length in terms of radians. In this case, my equation in this form now just simplifies to theta times r. So I can get rid of this whole thing. Now, if this is true, and I look at the circumference, the angle in radians needs to be equal to 2 pi, right? In order for this to be true. So because of that, 360 degrees, right? So for a full circle, the angle in degrees is 360, would have to equal 2 pi. So that's the easy way to remember the relationship between theta and pi. You say 2 pi from the circumference is equal to the full angle in degrees, 360 degrees. Now, once I have this relationship, I can convert all of these angles in degrees into radians. So I'll do a couple with you. So if I want to convert 90 degrees, right, that right angle, so I could say 90 degrees multiplied by 1, right? So this is how I convert units. I say 2 pi divided by 360. So since 2 pi is equal to 360, this is just multiplying by 1, right? So 90 divided by 360 is 1/4. So 2 over 1/4, that gives me pi over 2. So I get pi over 2 for 90 degrees. 45 degrees is 1/2 of that, so pi over 4. I get that there too. If I do that for each of these, right, so if I look at the 90-degree segments, I get pi over 2, pi, 3 pi over 2, and 2 pi. And it's convenient to draw this on a unit circle. And we'll do that, we'll look at this again from a unit circle perspective when we introduce sine and cosine. And then for 45 degrees, we said pi over 4. That's what we showed there. For 30 degrees, you can convince yourself that you get pi over 6. For 60 degrees, you get pi over 3. So I can draw the circle and show the angle in 45 degrees, or I can write pi over 4. Now remember, when we use units of radians, we don't write radians. We don't write anything afterwards. We intuitively know that this is going to be radians. It's unitless. When we write things in degrees, we write this degree sign, right? The little circle superscript to help us keep it distinguished. So when you tell someone the angle, if you're telling it to them in radians, you want to say it out loud, right? Whatever the value is in radians. Sometimes you won't actually have a pi term in your radians. You just say a number. So pi is like 3.14, right? So 2 pi is about 6, right? A 6-degree angle is very, very small. 6 pi is almost that full circle. So, sometimes you might get confused if it's in radians or degrees if the angles are very small to begin with. So it's small in both degrees and radians. But if the angle looks relatively large and you're giving me a small number, you should assume or actually ask, but most likely it's in units of radians. So, distinguishing the two verbally or by writing the degree sign is important, but in general, we don't write it for units of radians. So in the next video, we'll take a look at the unit circle again. We're going to build on this concept of degrees and radians, and we're going to help us to understand what sine and cosine are, and use a unit circle to help us remember a lot of the principles about sine and cosine.